Okay, this video is on chapter 16, section E, de Moivre's theorem. Here it is. In the blue box, coming at you from the textbook. In the white box, coming at you from the data booklet. So we don't need to memorize this thing. Honestly, it's not that complicated. It's super powerful. We can do a lot with this. So it's an extension really of what we saw previously, which was we saw what happens when we take cis theta times cis phi. We knew that that gave us cis theta plus phi. And if phi had been equal to theta, then this would have given me cis 2 theta. And if I multiplied by another cis theta, then I would have had cis 3 theta, and so on and so on and so on. So the rule says if you raise a cis to a power of n, then we just multiply the argument by n. And the modulus gets raised to the power of n. That's all it says. And here we have it in, we can see it at work in polar form, as well as in Euler form, as well as in just this other shorthand notation for polar form. Down below, there's an induction proof of it for positive integers. The book continues, I believe, for negative integers, as well as you can also extend this for rational powers. But we'll just take a quick look here at the positive integers. So we start off with the first positive integer, n equals 1. In that case, yeah, this is definitely true. Modulus z times cis of theta to the power of 1 is equal to modulus z to the power of 1 times cis of 1 theta. Okay, cool. Then we assume that a p sub k is true. So here we have the same statement written out, but with k's instead of n's. And then we think, what would happen to this one? What would happen to mod z cis theta to the k plus 1? Well, if we're raising it to the power of k plus 1, that means that we can break it up into a product, once to the power of k on the left, and then once to the power of 1 on the right. We know from the assumption up above that when we raise it to the power of k, we're going to get mod z to the k times cis of k theta. This piece on the right just comes down. Then, knowing the simple statement from previous videos, we know that we can take these two, multiply them together, and we're just going to add their arguments. And on the outside, we'll take mod z to the k times mod z, so that'll just be mod z to the k plus 1. And then finally here, we're just going to factor out the theta, and we'll get cis of k plus 1 times theta. We've got a conclusion down here. Again, referencing that p sub 1 was true, referencing the connection between p sub k and p sub k plus 1, that p sub k plus 1 is dependent upon p sub k, and then we're concluding that it's true for all n, which are positive integers. All right, so there's your induction review for the day. Let's move forward and do a couple problems using de Moivre's theorem. So we can now simplify these gigantic-looking complex numbers rather easily. This first one is just going to become, so it's going to be the square root of 2 to the power of 10, which is the same as 2 to the power of 5, which is to say 32, times cis of, it's going to be 10 times pi over 5. So that's going to be cis of 2 pi. Oh, but wait. I know what cis of 2 pi is. Cis of 2 pi is just 1. That's awesome. This whole thing is just equal to 32. For something like letter E in the bottom right, we're going to rewrite that cubed root as a power to 1/3. The cubed root of 8 is 2. And I'll have cis of pi over 6. If a number is given to you in Cartesian form, you're just going to want to convert it to polar first. So letter D, -1 plus I, that's going to have a modulus of the square root of 2. It'll be cis of 3 pi over 4. And then after that, again, it's pretty easy. Root to the -11th, might have to think about that for just a moment. But then it'll be cis of -33 pi over 4. We know that square root of 2 to the power of 10 is 32. We talked about that earlier. So I guess this is going to be 1 over 32 root 2 And then cis of negative 33 pi over 4, just kind of imagine where that is on your unit circle. We know that negative 32 pi over 4 is going to be back where we started from. So then it's just minus another pi over 4. Okay, here we've got a complex number z, which is 1 plus I, and we want to therefore write z to the power of n in polar form. Not too challenging. Z to the power of n is going to be square root of 2 to the power of n, or, I mean, I guess you could write that as 2 to the n over 2 if you want, whatever, times cis of n pi over 4. Now where this question gets a little more interesting, find the values of n so that this number here is real and so that this number here is imaginary. So for that, we're going to break up the cis, right? So we still got the square root of 2n, but now this is cosine of n pi over 4 plus I sine of n pi over 4. So if it's totally real, that means that this term here has got to be equal to 0. And for that to be equal to 0, what does n have to be? Well, we know that sine is equal to 0 whenever we are taking the sine of an integer multiple of pi. So in this case, to have an integer multiple of pi, we need n to be equal to 4 times some integer. For the complex for z to the n to be purely imaginary, similar idea, we need this term to be equal to 0. I know that cosine is equal to 0 at odd multiples of pi over 2. This one I think I should probably just write out. So n pi over 4 needs to be equal to pi over 2 multiplied by an odd integer. So that'll be 2 times some integer plus 1. And then just solve this for n. So in this case, we need n to be equal to a multiple of 4 plus 2. So anytime that n is an even integer, something interesting is going to happen in this case. All right, now let's look at one that's going to require us to use a bunch of trig. So if z is cis theta, prove that z squared minus 1 over z squared plus 1 is equal to I times the tangent of theta. That doesn't show up all the time, having a tangent involved. This is a pretty lengthy one. I don't feel like writing it all out. You don't feel like reading my handwriting for that long. So here it is. We're going to use, first we're going to change the z to cis theta. Then we're going to use de Moivre's theorem. So the cis theta squared is going to become cis of 2 theta. After that, we're just expanding cis to see cosine plus I sine. Then we're going to use some trig identities. We know that cosine of 2 theta is equal to 1 minus 2 sine of theta. That's what we've got on top. And the way they've chosen to do it on the bottom is to use the other identity, cosine of 2 theta is also equal to 2 cosine squared theta minus 1. The reason that those two were chosen in those specific places is to cancel out the 1s, right? Because we had a plus 1 here and a minus 1 at the end. And this had a minus 1 and a plus 1. So that was rather convenient. The next thing we're going to do is rewrite sine of 2 theta as 2 cosine theta sine theta. Did that in the numerator and the denominator. Now I want to interject a little bit. So for our next step, we are going to factor some things out. I think the obvious thing to factor out from the numerator is 2 sine theta, and from the denominator is 2 cosine theta. We can already see tangent popping up here, right? Because we've got sine over cosine. That's pretty nice. 2's are going to cancel. Awesome. So now we just need to show somehow that this part here is all equal to I, which that's not obvious at all. And here's what is happening kind of in this step. I don't think it's obvious from looking at it without thinking about it for a minute. So let's think together. The bottom is clearly cis theta. The numerator, not quite. It almost is, except I've got an I attached to the cosine and nothing attached to the sine, although there is a negative 1 there. So wishful thinking. I really wish that this I was not there. Let's factor it out. It doesn't look like there's an I here, but when you start thinking about it like this, is factoring out, yeah, I mean, we do have a power of I here, right? Because we have -1. So that is I squared sine of theta. And that's how we get this here. So I cosine of theta, that's directly there. And then this minus sine of theta, that's the same as plus I squared sine of theta. And then we notice that this piece here is just cis theta, but it has an extra factor of I in it. So we can pull that out, and that brings us here. And the cis's are going to cancel, and there we have it. That's I tangent of theta. All right, now what we've got going here is a very popular question type, so pay attention to this one. We're going to use complex number methods. I'm going to underline that because we're not allowed to just go to our trig formula sheet and try to pull identities from there to prove these two. All right, we're going to use complex number methods only. And the way that this works is I'm going to answer both of these at the exact same time. All right, so this isn't something that we do separately. It's always going to be simultaneously. Here's how we're going to do it. I'm going to not start off by thinking about cosine of 3 theta or sine of 3 theta. Instead, I want to start thinking about cis of 3 theta. So I've got cis of 3 theta, but using de Moivre's theorem, we can pull that 3 out, and we can rewrite this as cis of theta cubed. But what is cis of theta cubed? I mean, that's just cosine theta plus I sine theta cubed. And we can use binomial expansion to rewrite that. And we're going to break it up, as usual, into real parts and imaginary parts. Keeping in mind, of course, that right here, we're going to have an I squared, so that's going to become real. This part over here will have an I cubed. That'll stay imaginary. Next, we're going to set the real parts equal to the real parts and the imaginary parts equal to the imaginary parts. So I've got cosine of 3 theta is equal to this, and then sine of 3 theta is equal to this part. But now we can start using trig formulas to match the red expression here with the one down below, and the blue expression here with the one down below. Here's the work for that. I don't really have any commentary to add to it, but you can see now what I mean about doing this simultaneously by using cis. We can solve for both cosine of 3 theta and sine of 3 theta at the same time. So there's your work for part A. By the way, 2011, Time Zone 1, Paper 1 had a question that asked exactly this, part A. Moving on to part B. So hence, all right, so and even if you had no idea how to do part A on an exam, you can still do part B because they tell us, hence, meaning we're going to use these two facts to move forward with this. All right, so tangent of 3 theta, so that we know that's just going to be sine of 3 theta divided by cosine of 3 theta, and then we're going to substitute in the expressions that they gave us, and then from there it's just algebra and trigonometric identities. So as a first step, we can factor out a sine from the top and a cosine from the bottom. As a second step, and this seems kind of wild, but one way to do it is to insert a cosine squared plus sine squared into both the numerator and the denominator. We know that's just 1, right? And that makes it look at first like it's going to be way more complicated, but that enables us to combine some like terms. And then from there, we can redistribute that sine and cosine that we had factored out earlier. Dividing the top and bottom by a cosine cubed will give us this expression. And this is nice because now I'm seeing tangents showing up all over the place, right? Here's this 3 tangent, tangent cubed, tangent squared. And that's exactly what we're looking for. Remember, the instructions were to write tangent 3 theta in terms of tangent theta only. So that means tangent theta to any power. Now, if you're sitting there thinking, man, I would have never thought to do this step here, to put in that cosine squared plus sine squared. Or I would have never thought to, redistribute the sine cosine that I had just factored out earlier. Or to divide both top and bottom by cosine cubed. I don't think you're alone in that. This is a particularly disgusting manipulation of algebra. So if you found yourself in this position and you somehow had extra time on the exam, one thing you can try to do is to cheat, and I don't mean copy off of your neighbor. I mean figure out what the answer should be using the wrong method. I mean the problem clearly does say hence. So I need to use, as you said, I need to use this information in order to answer part B, but maybe I just want to know what the answer should be. So you can still use trig formulas, as we see here, using the compound angle formula for so tangent of A plus B. We can have this, and then using it again, or just using the double angle formula for tangent of 2 theta, we're going to rewrite each of those. So that gets us here. After that, I'm going to combine, because the numerator has tan theta plus this fraction, and then the denominator has 1 minus this fraction. So we're going to make that all one big fraction divided by another big fraction, noticing that they have the same denominator. So that's very nice. Those can just go away. And then when we combine like terms, we get the answer that we had on the previous slide, if you can read my handwriting anyhow. So that would give you a hint, at least, as far as like, this is what the answer should be. Can I manipulate to get it there? Now, I don't know if you'll have that kind of time, but at least it's an idea to keep in the back of your head, even though this is not at all the method we're instructed to use. So this would be worth 0 marks on its own. It still might give you a hint as to the right direction to move. Now moving on to letter C. Hence, again, oh my gosh, hence solve these two equations. Now, so like, you know, what is the connection here? You know, we've been doing this problem about complex numbers and trigonometry, and now all of a sudden we have these polynomial equations which look impossible to solve without a calculator, right? But if we look closely, this is 4x cubed minus 3x, and this is 4 cosine cubed minus 3 cosine. So if we let x equal cosine of theta, there's clearly a connection. Over on the right is less obvious. Let's hang on to that for just a moment. Let's just do the left-hand side. So we're going to let x equal cosine theta. Therefore, 4 cosine cubed minus 3 cosine is equal to negative 1 over root 2. Well, that needs to be cosine of 3 theta using our information above. So now we're just going to solve that trig equation, which isn't terribly challenging. Now, it is not explicitly stated in the question, but I think a good assumption is that we want theta to be in between 0 and 2 pi. So that means that 3 theta, which is what we're actually solving for here, should be between 0 and 6 pi. So when I'm mentally doing this here, figuring out, okay, what value for 3 theta would have a cosine of negative 1 over root 2, or negative root 2 over 2 is how I like to see that. I'll get these values out, and then we just divide each of those by 3 to get a theta in between 0 and 2 pi, which at first glance seems like there is 6 solutions, but really pi over 4 is going to be the same as 7 pi over 4 in terms of what its cosine value is. Cosine of pi over 12, 5 pi over 12 is the same as cosine of 19 pi over 12, and cosine of 11 pi over 12 is the same as cosine of 13 pi over 12. And it certainly makes sense that there should only be 3 solutions here, because recall that we're solving a cubic equation, so there needs to be 3 at most. Now, as for this one on the right, x cubed minus 3 root 3x squared minus 3x plus root 3 equals 0. That doesn't seem to have an obvious connection to either of these. Well, let's see what we can do here. If we move some things over, we've got this. Okay, what else could we do? Well, we could try factoring out that root 3, maybe, I guess. Seems fair. We can then divide by, oh, wait a second now. Now I'm seeing a connection, because this looks just like the answer that we got for the tangent of 3 theta back in part B. So in this case, if we let x equal to tangent theta, we're good to go, where root 3 is going to be equal to tangent of 3 theta now. And then we solve that in the same way, and again we get 3 solutions at the very end, which is good since we were solving a cubic equation. Now, I'm not saying that this problem is fun. I mean, there's a lot of trig and algebra that we had to do, a lot of hoops to jump through. However, I do think it's really neat that we can use complex numbers to solve these very challenging polynomial equations that otherwise, as I said earlier, we would have no option but to approach these with a calculator. And yet now we can get exact values out. Now our exact values are cosine of whatever angle or tangent of whatever angle. We don't know what those values are as, decimal approximations or anything, but that's okay. We have exact values. So I think this is just a wonderful connection of a few different themes from the course. And for our final question, here's one that's very, very similar to 2009 Time Zone 2 Paper 1. And you'll see examples of this in like every single HL math textbook. We'll have something that looks like this right here. So let's do it. All right, so this is also going to be a massive amount of work, so I'm not going to write it out. Let's read through and talk it out together. So remember that we're trying to prove this here. So for starters, what is z to the power of n? Remember that z is equal to cis theta, so z to the n is going to be cis theta to the power of n. We're down here now. We're going to use de Moivre's theorem to rewrite that as cis of n times theta. And on the right-hand side of this, similar with 1 over z to the n. 1 over z to the n is just z to the negative n. So we're going to use de Moivre on that. And we're here. Now remember that cis of negative theta, the cosine of negative theta is the same as cosine of theta. Whereas the sine of negative theta is negative sine of theta. Right? So that's what's going to happen when we get down to here. Cosine of negative n theta just changes into cosine of n theta, whereas this I sine of negative n theta becomes negative I sine of n theta. Putting things together, I notice that these two are going to cancel out, leaving us with 2 cosine of n theta. Roman numeral 2, I don't even know why it's a question. Obviously, we're just letting n equal 1, so that's pretty boring. Roman numeral 3, they're telling us just use the binomial expansion theorem. Okay, so we're going to do that. Z cubed plus 3z squared times 1 over z, blah, 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 blah. Simplify, simplify, simplify. We get here. Noticing that we've got z cubed plus 1 over z cubed and 3z plus 3 over z. Those two are going to work in pairs now for Roman numeral 4. Let's just scroll up to see the question again. We're going to show that cosine cubed is equal to this. Well, for starters, using the result that we just worked out, we've got this line. We're factoring out the 3 from the red pair. Using what we know from above, this needs to be equal to 2 cosine of theta. So when we're cubing that, that means we're really cubing 2 cosine of theta. So on my left-hand side, that's just 2 cubed times cosine cubed of theta. All right, great. And then my right-hand side, again, subbing in here and here, using the results from part A, Roman numeral 1. We now have 2 cosine of 3 theta and 3 times 2 cosine of theta. So that's 6 cosine of theta. A little bit of algebra, and we got the result that we wanted. Roman numeral 5, hence, show the cosine cubed of 13 pi over 12 is equal to this. They even give us a hint for how to break up 13 pi over 12. Okay, whatever. We're just putting in 13 pi over 12 into theta here and here and here. I see compound angle identity happening right there. And other than that, we're just filling in values of cosine that we should know. So nothing else to really say about that. Looking now at part B. So part B is really similar to part A, right? Instead of finding an expression in terms of cosine, now we've got something in terms of sine. And the difference on the left is instead of a plus, we've got a minus. So we're going to approach that in the exact same way as we did before, except this time we'll find that the cosines are going to cancel each other out in the end, rather than the sines. moving forward. Hence, with the sine cubed, it's the exact same plan as we had before. Now we're going to be cubing 2I sine of theta, and we're also going to be expanding the expression that we had with z's using binomial expansion theorem, simplifying the I cubed out, and then moving everything over to the right-hand side, and we've got an expression for sine cubed. So both this and earlier, they rely upon us cubing a number while it's written in two different forms, in a trig form as well as in a complex number form. And by approaching that in two different ways, we are able to arrive at the desired result. It's neat. And finally, for part C, we've got to hence show that sine cubed times cosine cubed is equal to this expression here. Well, we've already figured out an expression for sine cubed. We've already figured out an expression for cosine cubed. So we're going to multiply those two together, use the compound angle formulas again. So I see that happening here. So that's where this theta minus 3 theta is coming from. Now theta minus 3 theta is negative 2 theta. So this is sine of negative 2 theta, which becomes negative sine of positive 2 theta. And from there, we're just going to combine like terms, and we got it. Once again, really lengthy, quite annoying, but these pop up in at the very end of paper 1 more often than you might prefer. So it's worth looking over these. Anyway, that's the Moivre's theorem. It's a ripe topic for induction. It's really good for, I mean, like the basics of it are really easy. Like I'm sure you'll be able to just take the exponent and then make that a coefficient of theta. And there are a lot of problems that just rely on you doing basically that. There's plenty of problems where there's marks to be scored just for writing a simplified version of some complex number to like the power of 11, and you just use de Moivre and it's done in a few seconds. But then there are also some more challenging applications, so I wanted to really push that a little bit in this video. Anyway, that's all. So don't be intimidated by this. Yes, there are challenging applications, but a lot of them are not. You'll see when we practice in class. All right, that is all. Hope you enjoyed. Take it easy.